All right, so this is it. Then we are told it is displaced by A. X is equal to 0.10 meter. B, X is equal to 0.05 meter. C, X is equal to 0. And D, X is equal to negative 0.05 meter. We have to find the force acting on it and its acceleration. So find force acting on it and the acceleration. Okay. So this is the problem of the day. Let me check attendance then. So Akuya, Adoma, Akuya, Amma, Carl, Herbert, Lizzie, Len, Ishra, Stephanie, and Yaba. These are the few participants who are not tired. The rest are tired. Anyway, some of you two are tired, but you are forced by your parents to come. Do I mention names? Those of you who are tired and forced by your parents. So question 1. So A, if the displacement is 0.1, what will be the force? What will be the acceleration? How do we determine the force acting on it? By using Hooke's law. So F is equal to minus Kx can help us determine the force. Because the question also gives us the spring constant. We are told the spring constant is 130 Newton per meter. So K is equal to 130 Newton per meter. Another way of determining the force is using F is equal to the acceleration, okay, the mass times the acceleration. This will also give you the force. So quickly, let's use F to find, let's use the first equation and confirm your answers using the second equation. Let's see if you get the same value. Start work. And I'm giving you, I think 5 minutes will do. We have up to D. So start work. It's 3-9. 3-9. Please go through it because I'll call you to share your answers with me. Okay, so Charlotte. For A, what did you get for force and for acceleration? For A, where displacement is 0.1, what did you get for force and for acceleration?
For the force, I had 3.5.
For the force.
And acceleration, yes.
And then for acceleration,
Acceleration, I had 350.
350.
And no.
I mean, for A, what did you get for force and what did you get for acceleration? Okay, Len, what did you get for force? What did you get for acceleration?
Please, I'm still on it.
All right, then let's solve it. We need to finish SHM today. So F would be equal to minus of K. K is 130 Newton per meter times displacement of 0.1, which is 1 on 10. So this is equal to minus 13 Newton, or by magnitude 130 Newton. Acceleration of a loaded spring is given by minus K on M times the displacement. Okay, before we talk about acceleration, this same force can also be calculated using MA. Okay, then we need to find acceleration before. So if A is also equal to A is minus K over M times the displacement. K is 130. What is M? Let's check what we were given for the mass. Let's check whatever we're given for the mass. So we are told that, okay, a 0.3 kilogram mass, so 0.35. So the mass is 0.35 kilogram times a displacement of 0.1. And this must be equal to acceleration of minus 37 point something. Let me check.
0.14.
Pardon?
0.14.
Okay, so this is 37 minus 37.14 meter per second squared. In fact, if you bring minus, you are correct. If you don't bring it, you are correct, because the minus indicates direction. Okay, but the magnitude of the acceleration is actually 37.14. So is the force too. So if I use this to calculate for the force, then F would also be equal to 0.35 times acceleration, which is 37.14. And you need to get an answer which is close to 13 Newton. let's confirm. 0.35 times 37.14. And this is approximately 30. So that is the way out for all the three displacements. Okay. So the only varying factor is the displacement at various. Now, when the displacement x is an extension, x is positive, and this is it. When I suspend a load and the load stretches it, okay, this is extension. If it's a compression, it is being pressed, okay, together. Then the displacement is taken as negative. So if you see the negative and then the positive, that is basically what it means. Any question? So I'll leave the three.
Extension is negative.
You see, in most cases, extension, the displacement is an extension. When we are compressing, that is when it is. So if you see a negative of the extension, then it means it's a compression.
Okay, thank you.
In most cases, it's an extension. All right. So you complete the rest. I'll post the answer on the platform for you to use it as a guide. Okay, so the energy possessed by a body executing simple harmonic motion. An oscillating body, okay, by virtue of its movement has, or by virtue of its velocity or movement has kinetic energy. Then by virtue of its position or displacement has potential energy. So when the body is displaced, by virtue of its velocity, it has kinetic energy. By virtue of its displacement with time or from the equilibrium position, if it is displaced by this amount, its position from the mean point, okay, gives us the potential energy possessed by the body. So if this is an oscillating body, when I displace it, by virtue of its speed, it has kinetic energy, and then by virtue of its position from the mean point. Example, an oscillating pendulum, mean point, MP. When I displace it to this distance, if it is now here, this is the displacement Y. So by virtue of it being displaced from the mean point, gives it potential energy. By virtue of the velocity it has, gives it the kinetic energy. All right. So the total energy possessed by an oscillating body is the sum of its potential and its kinetic energy. So energy possessed by a body, energy possessed
Sir, please, you're on mute.
Okay. So its kinetic energy is by virtue of its speed or velocity and its potential energy. Energy is by virtue of its displacement. Its displacement or position from the main point. Okay. So that's the energy possessed by an oscillating body. Partly kinetic and partly potential. Now, a change in one form of the energy is again to the other form of energy. So energy possessed by an oscillating body is said to be conserved, meaning no energy is lost, because when one drops, it's again to the other. So no energy is lost. A loss in kinetic energy is a gain in potential energy and vice versa. Okay. All right. So let's look at. Are you done writing?
No, please.
Let's go through the mathematics of each of the energies, and then we look at the total energy. Let me know when you finish, okay? Are we done?
Yes, please.
Yes, please.
Okay. All right. So let's look at a simple pendulum. and analyze the energy possessed. So once it possesses both potential and kinetic energy, then the sum of these two is the mechanical energy. So the energy possessed by an oscillating body is a mechanical energy. Now for an oscillating body, a simple pendulum. This is the mean point. If it is displaced to one side, to one extreme, why? And this is it. Because the body is oscillating, okay? Because it's an oscillating body. You realize that as it moves over here, when it gets to the extremes, these are the extremes. Another extreme. When it gets to the extremes, the body stops. You ask yourself, why is it that when it gets to one extreme, it doesn't continue but stops, comes to the other part, and then where it gets to, okay, and then stops, means that at that point, its speed with which the body is moving with drops to 0. So when it is moving from the mean point to the extremes, at the extremes, the velocity is 0. Okay, and we saw that for an oscillating body, its minimum velocity occurs at the extremes. So if the velocity at the extreme is 0, kinetic energy has to do with velocity. Then it means Ke, kinetic energy, is also 0. Wherever velocity is minimum, kinetic energy would also be minimum. Wherever velocity is maximum, kinetic energy would also be maximum. So where does the maximum velocity occur? For an oscillating body, where does the maximum velocity occur?
Point.
All right, so when crossing the mean point, please don't just say the mean point. When crossing, if you don't qualify it, then the argument is that you have a look at it. It is here. At this position of the body, it doesn't even possess velocity to have kinetic energy. So it is maximum when the body or particle is crossing the mean point. Okay, so maximum velocity occurs when the body is crossing the mean point. So velocity is maximum at the mean point. V equals maximum. And so kinetic energy would also be maximum. So at the extreme, velocity is 0, kinetic energy is also 0. When crossing the mean point, velocity is maximum and Ke would also be maximum. Okay. Now, potential energy. Potential energy is by virtue of the body's displacement. It's by virtue of the body's displacement. So, Inshira, Madam Kwa Inshira, are you there? Inshira is gone. I hear you. Okay, so Herbert,
Yes, sir.
If
Yes, sir.
if PE is by virtue of the displacement, the potential energy possessed by the body is by virtue of its displacement. Where would potential energy be maximum and where will it be minimum?
Sir, please, can you repeat again?
If potential energy possessed is by virtue of the body's displacement, where will it be maximum? Where will it be minimum? Where would potential energy be maximum? Where will it also be minimum?
Sir, because the kinetic energy is 0.
No, you didn't understand the question. Where? Where will it be maximum? Where would PE be maximum? Where would PE be minimum?
Okay. Sir, please, VE. Sir, VE will be minimum.
Okay, you will listen and watch. You are not so clear with the question. Ekuyadoma.
Mr.
If potential energy is by virtue of the body's displacement, where will it be maximum? Where will it be minimum?
Mr. Please, it will be minimum at the main point and maximum at the extremes.
Thank you. So, Herbert, because is directly proportional to displacement, okay, if displacement is 0, then it means PE would also be 0. So, PE is 0 or minimum at the mean point, then PE is maximum at the extremes. PE is maximum at the extreme. And Charlotte,
Yeah.
why is potential energy maximum at the extremes? Why? Just two answers, so 2-word answers. Why is PE maximum at the extreme, Charlotte? Okay, Len, why is PE maximum at the extremes? Oh, Len.
Because displacement is maximum at the extremes.
Exactly. And this maximum displacement is known as the what? Len, this is known as the what? Amplitude. So the whole answer is that at the extremes, the displacement y is equal to the amplitude. Is that okay? Please, are you okay?
Yes, please.
All right. Now, for a simple pendulum, okay, before I move on to a simple pendulum, I said a loss in one form of energy is a gain to the other form of energy. And this is what I mean. At the extremes, velocity is 0, meaning potential energy is, meaning KE is also 0. So KE is 0 here. Over here, PE, KE is maximum. Meaning that when the body is moving to the extremes, you have its velocity decreasing because it is 0 here. So decreasing, it is maximum when it is crossing the mean point. Okay, so when it is moving to the other extreme, the velocity will be decreasing. By the time it gets to the maximum displacement or the amplitude or the extreme, it has decreased to 0. Now, if kinetic energy is decreasing, what about potential energy? See, we are picturing the body moving from the mean point to the right. So it is moving in this direction. If the body starts from this point, when it is moving to this extreme, extreme 1, the body's velocity is decreasing. But what is happening to the displacement? If the velocity is decreasing, what is happening to the displacement? Yes, it is increasing. So if the displacement is increasing, then the potential energy would also be increasing because PE is directly proportional to Y. So look, the same direction, KE is decreasing because velocity is decreasing. But PE is rather increasing. By the time we get to the extreme, because the velocity is 0, kinetic energy is also 0. But at that same position, the displacement is maximum. And so potential energy is also maximum there. So a loss or a drop in one form of energy is a gain in the other form of energy. Now, when it is returning from the extreme, velocity is 0, kinetic energy is 0. But this is what is happening. Okay, this time displacement is decreasing. Displacement is measured from the mean point. So displacement is decreasing, but meaning potential energy is decreasing, but velocity would also be increasing. Don't forget, the velocity is given by omega times a squared minus y squared. So when y is 0, at the mean point, we have the maximum velocity. So if y is decreasing, meaning it is gradually drawing to 0, that is when we'll be experiencing maximum velocity. But at the same positioning, y is decreasing, and so potential energy would also be decreasing. Okay, so at the extremes, so for an oscillating body, its total energy, which is KE plus P. At the extreme, the total energy possessed by the body is equal to potential energy because KE is 0. At the mean point, the total energy possessed by the body is kinetic energy because PE is 0. Okay, so when you pick any 2 points, extreme, this point, energy is never lost. What is lost as KE will be a gain for PE at the extreme. When we come to this point, what is lost for potential energy is a gain to kinetic energy. And so the total energy is always conserved. When you pick half of the displacement at the midpoint of the whole displacement, we'll have half of it being kinetic, half of it being potential energy. So the total energy, no energy is lost. A loss in one form of energy is a gain in the other form of energy. Please, is it understood?
Yes, please.
All right. As one is dropping, the other is increasing. As the other is increasing, the other is also decreasing or dropping. And so at every time, no form of energy will be lost. So we said that the kinetic energy is by virtue of the displacement of the body. Sorry, is by virtue of the body's velocity. So if you want to determine the kinetic energy at any point, it is equal to KE is half, KE is equal to half mv squared. So when the body is here, and I'm to calculate for Adoma.
Mr. Dear, please, I don't I don't get why at the mean point V the kinetic energy is the maximum and then at the extreme point is equal to 0. Because you see kinetic energy is by virtue of the potential energy is by virtue of the body's position.
The all displacement.
Pardon?
All displacement.
Or displacement.
Position or displacement.
That's for the potential energy.
Yes.
Okay.
So are you okay?
Yes.
Is it explained?
Something like that.
What is the question? You don't understand why?
Is it because the potential energy is the energy possessed by body by virtue of its position? I was expecting that when it's at the mean point, it should have like that should be the maximum potential energy.
No,
Because it's by
you see, the energy possessed by virtue of the body's position or displacement. Position is displacement. So meaning if the body is at the mean point, Charlotte, what's the displacement? What's the displacement at the mean point?
0.
0. And so potential energy here must be 0. Is that okay?
Yes, please.
When the body is at the extreme, we have the displacement is equal to the amplitude. And so potential energy will also be maximum there. Okay. As for kinetic energy, it is equal to half mv squared, our old formula, or because V is equal to omega times a squared minus y squared. When we square this, we'll have V squared equal to omega a squared minus y squared. So it means that Ke for an oscillating body, its kinetic energy can also be half m omega times a squared minus y squared. All right. When y, the displacement y is equal to the amplitude, Charlotte, where is the body located under this condition? Where is the body located under this condition when y is equal to a, Charlotte? Oh, I need a quick response. The extreme. Put y for a here and see what will happen. If you put in a in place of y, you have whatever within the bracket being equal to what? Charlotte, I'm dialoguing with you.
Yes, please.
It's 0, right? And if this is 0, the whole thing will be 0, confirming the point that at the extreme, kinetic energy is 0. All right.
Yes, please.
So for an oscillating body, we can determine its kinetic energy based on its displacement using this relation. Okay, we can find V and then put it within this equation to find Ke. How do we calculate for its potential energy for a simple pendulum? For a simple pendulum. So for a simple pendulum, how do we calculate for its P? This is the mean point. The body is here. This L length of the string, L. When the body is here, you realize that as the body oscillates, look at the body. When it is, assuming it's even flat, like this, when it is moving, oscillating, it looks as if it is moving up. It is covering a vertical height. So look at it. When it's at this position, when I trace the horizontal part, it looks like this. But when it gets to any point or at any displacement, you realize that the body is covering a certain vertical height. So at every position, there seems to be the body covering a certain vertical height. Is that okay? Please, do you see the illustration?
Yes, please.
Look at the head of it. So when it is moving, it is like covering a certain vertical height h. We know potential energy P is equal to mass times vertical height h. Potential energy depends on gravitational energy. So this is actually called gravitational potential energy. Okay, because we have another form of energy which we'll talk about. So the gravitational potential energy possessed by a simple pendulum, PE or GP, is given by its mass times gravity times the vertical height covered. So when the body is here, it seems to cover a certain vertical height, this. And this is also almost the same as h here. So we are talking about this vertical height h covered. Knowing this would help us determine the gravitational potential energy possessed by the body. It's not directly due to its displacement when the body is oscillating. So let's assume the angle the string covers with this vertical, or the mean point is theta. Now our point of interest is we are looking for this vertical height h covered to determine its gravitational potential energy. This length L length of the string is the same as this length of the string. So if this is L, from this point to the center is also L. All right. This is also L. Now, please pay attention and then watch this. If I draw this vertical or horizontal line from the object, I have opposite side to this angle. This is the opposite side to the angle. This opposite side and then this the adjacent side must be perpendicular. So if this whole height is L and this is H, please, what will be the distance from this point to the fixed point, to the support? If this whole length is L and the vertical height covered by the body is H, what will be the distance from here to here? Yes, Apia.
L minus
Follow
H.
L minus H. So this is L minus H because this whole length is, we have L, assuming plus, okay, so let's take it this way. Assuming this is X, from here to here is X, and this is H. It means L is equal to X plus H. All right. Meaning that if you are looking for maybe H, because we are interested in this vertical height covered, H is equal to L minus X, isn't it? Class, are you following? Are you following? Hello, give me feedback. Are you following? Oh, they can't hear me. Can you hear me? Hello? Hello?
Hi.
Hi.
Can you hear me? All right. So if H is equal to L minus X, can we, when we take the cosine of the angle, cos of theta, cos theta here would be equal to X over L. This X, cosine of this angle, X over L. Therefore, X is equal to L cos theta. If X is equal to L cos theta, then we can say that H is L minus L cos theta. So that we can factorize L out and we have 1 minus cos of theta for H. Therefore, the potential energy, by having this, we have had an expression for the vertical height covered in terms of the length of the string and then the angle it makes. Therefore, the potential energy is given by M J H. H is this, L 1 minus cos of theta. So if we are told that maybe the angle for a simple pendulum, the angle the body makes from the mean point is 30 degrees. And the length of the string L is 1.5. Calculate the potential energy at this position. The position refers to the angle made, because if the body is still at the mean point, then it means that the angle it makes with the mean point is 0. But once there is an angle, then it means the body has moved. Therefore, using this, you can determine the potential energy when you are given the mass of the body, the length, the angle, and then the acceleration due to gravity, which is constant. So for a simple pendulum, if you want to calculate for the gravitational potential energy. This is the relation. Understood?
Yes, please.
Okay. As for its kinetic energy, Ke equals half mv squared. Knowing v to be equal to omega a squared minus y squared. When you find v, you can easily determine the kinetic energy. So the total energy possessed by the body at any point must be equal to its kinetic energy plus its potential energy. However, if it gets to the extreme, the total energy possessed is potential, and at the mean point, the total energy possessed is the kinetic. All right. Then if there is a, let's draw energy graph in terms of its potential energy and its kinetic energy. The energy graph. Charlotte, do I clean this?
No, please.
While you watch the video, or you not watch?
I'll watch, but then I want to write it so that I'll be following instead of writing it again.
Okay.
Please, I'm done.
Okay. So
Thank you.
the energy graph in terms of so for the energy graph, we are looking at the body's energy at the mean point and the body's energy possessed at the extreme. So this vertical line represents mean point. Then we have at the extremes. Okay. Now we pick the energies one at a time. Let's draw a vertical line at the extremes. Then one is bigger than the other. Yaba, you here? Yaba. Or Yaba is gone.
Yes, please. Yeah, bye.
Hey. We are 5 at the moment. Hey, we are say. Oh boy. Eddie. In fact, you are pushing me to stop online.
Oh,
Yes. You are pushing me to stop online. I find it difficult dealing with serious, yes, students who are not regular and all that. It worries me. Okay, so at the extremes, which of the energy is maximum?
Potential.
So potential energy is maximum at the extremes. You see, the vertical line indicates its maximum. You see, easy, Madison,
Yes, Mr. Dear.
mute yourself, else I'll add you to the sounds to tell
Yes.
to add Addison. If these are, yeah, this is the main point. But if these are marked or graduated scale, and this one, okay, let me even, okay, graduate this instead. They indicate levels of energy, meaning if you are grading them 0, 1, 2, 3, 4, blah, 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 up to, it means that if we are talking about maximum energy at the extreme, yes, it is potential, but this energy will be indicated because it's maximum. We won't this represent this energy from 0. We'll pick it from the maximum point to indicate that this kind of energy is maximum at the extremes. So if it is maximum, PE is maximum at the extreme. When we get to the mean point, what is its value at the mean point? What is potential energy's value at the mean point?
0.
0.
Look at how the graph will look like. It starts maximum from the extreme, then dropping. By the time it gets to the mean point, it has dropped to 0. To show that this energy is maximum at the mean point, at the extreme, minimum at the mean point. Then at the other extreme, it is also maximum. So 0 from the mean point, increasing. By the time we get to the other extreme, it is also maximum. So this is the energy graph for potential energy, for P,
Mr. Dear,
in terms of displacement.
please, is it a straight line graph?
No, it's a curve, meaning it is maximum here at the extreme, decreasing. By the time it gets to the mean point, it has dropped to 0. Then at the other end, it's also maximum at the other extreme. So increasing. By the time it gets to this point, it is maximum. All right.
Okay.
So this is for potential energy, gravitational potential energy, P. Then what will you say for kinetic energy? What is its nature at the extreme?
0.
0.
So kinetic energy must start from the 0 energy point here. Must start from 0. Then it is maximum when crossing this. So 0, when it's approaching the mean point, what happens to KE? When it is approaching the mean point, what happens to it? Is it increasing or decreasing?
Increasing.
Increasing.
So 0, increasing. By the time it gets to, it crosses the mean point, it is maximum. So 0, increasing. increasing, and maximum here. Then when it is getting to the other extreme, what happens to it? From the mean point to the other extreme, it is decreasing. Okay, so this is how that would also be. Maximum decreasing. By the time it gets here, it is 0. And this is for kinetic energy. Now, there is some peculiar parts. When you draw a vertical line to link the two graphs, a vertical line linking the two graphs, this vertical line linking potential energy graph, kinetic energy graph gives us the total energy possessed, which is the mechanical energy. Now, the point where the graphs intersect, the point where the two graphs intersect here and here are points where the two graphs are the same or are equal. So over here, at this point, PE is equal to KE, and at this point too, PE is equal to KE. So this is the energy graph in terms of displacement. Energy graphs in terms of displacement. Is it? I'm sure it is understood.
Yes, please.
So at points A and B, both PE and KE are equal.
Lydia, please, the red marker is not clear.
I agree, Adoma. The red marker is clear. Charlotte, put on your glasses. Charlotte. Hello. Hey, ask me. Class, can you hear me?
Yes, please. Oh, Mr. Chair, please, I can't see with the red marker. I don't know what my glasses too.
I'm coming. Let me pick this call and get back to us. Okay.
Hi.
Okay. All right, Charlotte, what I've written here is that at point A and B, both PE and KE are equal in value. Okay. So at least if you cannot see, at least you can hear, isn't it? All right. So this is the energy graph. Now let's look at this is for energy graph for simple pendulum and also applies to a loaded spring. Now, when we look at loaded spring, for a loaded spring, its energy relations are a bit different because of spring constant and all that. So let's look at potential energy and kinetic energy for a loaded spring, right? So for a loaded spring, or for a loaded spring, its kinetic energy it still have mv squared. So yes, a loaded spring also possesses both PE and KE. But for a loaded spring, this is known as elastic potential energy. The energy it possesses is not gravitational, it is elastic potential energy. And look at it. Okay. What the elastic potential energy is the energy or is the work done in stretching or compressing this. So we define elastic potential energy of springs or elastic material. So here we won't state it as PE but EP, where EP equals elastic potential energy. So springs possess or elastic materials possess elastic potential energy. And a simple pendulum is gravitational potential energy. So for a loaded spring, yes, it also possesses EP plus KE, which is equal to the total energy possessed by the body, which is the mechanical. Now, its elastic potential energy is also by virtue of the displacement or the extension. When I stretch it small, okay, when I stretch it much, so the elastic potential energy is also by virtue of its extension or displacement, and kinetic energy is also by virtue of its speed. All right. All right. Now, class, can you hear me?
Yes, please.
Okay. Kinetic energy. Expression for the kinetic energy is still half mv squared. However, v squared is equal to omega times a squared. Okay, let me make this capital A, amplitude, minus y squared. So when we substitute this, we have half m omega a squared minus y squared. Okay, if you recall, on a period of oscillation of a simple pendulum, we said that the spring constant K is equal to m omega squared. Do you remember? Do you recall this formula? And so the kinetic energy possessed by a loaded spring can also be equal to half K times a squared minus y squared, where K is equal to the spring constant. Spring constant. So either you express the kinetic energy as this or as this. A is the amplitude, Y is the displacement. Amma.
Mr. Yeah, please, the first equation, the K is equal to half mw, but spring constant is equal to MW is the power 2. But you've substituted it into the MW. But the W is
Omega, don't call it W, omega.
W. Please, but the omega in the first equation is not squared. So why?
No, it is squared, it is squared, it is squared. It is from here. V, you have V is equal to square omega A squared minus Y squared. So if you square this, V squared will be equal to square of this time A squared minus Y squared, isn't it? So
Yes.
it has to be squared here. So it is also, this is squared. So this is the energy, kinetic energy for a loaded spring, either this or this. Now, what is the elastic potential energy? As if for springs, we talk about the elastic potential energy. So now the elastic potential energy is defined as the work done, the elastic potential energy of an elastic material or body is defined as the work done in compressing or extending or stretching the material. So the elastic potential energy of a material is the work done in compressing or stretching. Stretching is extension, okay, the material. So, oh, my earpiece will not allow me today. When it goes off, I'll still teach. So here we take spring. When unloaded, and when loaded, to cause stretching or extension or compression. Now, when loaded, the restoring force acting on the material is F and acts opposite to the extension. So F is the restoring force because the extension is downwards. It's in a downward direction. When unloaded, the restoring force acting on it is 0 because there's no load. And so there's no restoring force, right? Now, what is work done?
Yes, please.
Work done Can you hear me?
Yes, please.
The work done in stretching this is equal to the average force, F average, times the distance, which is the extension when there is a load. So the work done in here, we are stretching it. Okay, which is the elastic potential energy possessed by the spring is equal to the average force times the distance the load covers. The distance the load covers is the extension X. Now, what is the average force? Here, we are looking at the force on the spring when there is no load and when there is load. So the average of this is equal to, when there's no load, the force acting on it is 0. When there is load, the restoring force acting on it is F. Because we are talking about average, sum of this divided by 2. So F average becomes F on 2. Therefore, the work done in stretching the spring is equal to the average force F over 2 times the extension X. So here it means when we draw the equilibrium position, it means that this is the extension when the load is suspended. So this becomes the work done. Please, are we okay? Are you okay with this? The work done.
I'm not okay with
Class, are
where
you
the
okay?
X begins.
So what is F? F is Hooke's law. F is Hooke's law given by Kx divided by 2 times X. Meaning the work done in stretching the spring, which we have called as elastic potential energy, is equal to half Kx squared. Half Kx squared. Now, its kinetic energy, the extension, we represented that by Y. X, it's not X, it's Y. So let's also change the X to Y. We want to create a uniform expression. So we are changing all expressions, displacement to Y. So the
Mr.
Hooke's law,
Are we
Ky. So that we have the elastic potential energy equal to half Ky squared. Appear, Charlotte.
Mr. Please, are we still talking about the same thing?
Charlotte, speak up or else I can't hear you.
Are we still talking about the same thing?
Charlotte, are you
Are we still
talking?
talking about the average? Yes, please. Can you
Oh,
hear
I
me?
can't hear you.
Oh, good. Amma, please, can you hear me?
Charlotte, I'm listening.
Yes, please.
Okay. Please, I was asking if, like, we are still talking about the average force, but then this time we are just representing X. So we are replacing X with Y.
Yes.
So it's still the same thing.
It's still the same thing. We are only
Okay.
representing the extension, okay, by Y instead of X because of our earlier relation.
Yes, please.
Okay. And so the elastic potential energy possessed by a spring, a loaded spring, is equal to half Ky squared. It means that, you see, since K is constant, spring constant, it means that elastic potential energy EP is directly proportional to the square of displacement, Y squared. Is that okay? Because half K is a constant. We can also rewrite this as EP is equal to half, since K is equal to, oh, today my earpiece. All my earpiece are disappointing me. But let's continue. Half, since K is equal to M omega squared, it means that EP can also be half M omega squared Y squared. Half M omega squared Y squared. So this is the expression for elastic potential energy. If you have any question, ask before we continue. All right. Now, Charlotte, can I turn it and continue?
Yes, please.
I'm coming. Let me adjust my volume and get back to. Okay, the volume is maximum 2. Amma, can you hear me?
Yes, please.
Hey, I can't hear anything. Oh. I'm coming. Let me. It's done now. All right. So if we are looking at a loaded spring and the total energy it possesses, which is the mechanical energy? The total energy possessed by a loaded spring, E total, is equal to its kinetic energy plus its elastic potential energy. And this is equal to half m omega squared a squared minus y squared plus half m omega squared a squared, which is this one, the elastic potential. This is not y squared, a squared, y squared. I'm talking about this one, the elastic potential. So when we add everything, we have half m omega squared a squared minus half omega m omega squared y squared plus half m omega squared y squared. These two would cancel out. So its total energy, which is the mechanical energy, is equal to half m omega squared a squared. Since m omega squared is equal to k, we can also say that the total energy possessed by a body executing SHM is also half k a squared, meaning the total energy is directly proportional to the square of the amplitude. That is why when we drew the energy line, the energy graph, okay, we had P to look like this, KE to look like this. And when we drew the line, we said this is the total energy. Here, look, we connected the total energy to the amplitude, the maximum. We connected it from the maximum displacement. It's a function of the maximum displacement, the amplitude. Okay, so ET is directly proportional to directly proportional to the square of the maximum displacement. Please, any question? Any question? So we've learned 3 stuffs. The first one is that for a simple pendulum, its kinetic energy is still half mv squared, but you don't lose sight of the fact that v squared is equal to omega squared a squared minus y squared. Then its potential energy, gravitational potential energy, loaded, please, I said simple pendulum. So let me clear. Simple pendulum. Then its gravitational potential energy is given by mgl 1 minus cos of theta. For a loaded spring, its kinetic energy, Ke, is half m omega squared a squared minus y squared, or half k a squared minus y squared. Then PE, elastic potential energy, is given by half m omega squared y squared, or half k y squared. Meaning, for elastic potential energy, this is directly proportional to the square of its displacement. Then the total energy, ET, is also equal to half m omega squared. But this one, similar to elastic potential energy, but this is a function of the amplitude, a squared. Meaning ET is directly proportional to the square of the amplitude, or ET is equal to half a squared. So these are the facts of today's lesson. All right. Please, any question? Any question?
No, please.
All right.
Okay.
Okay. All right. So there is something left, but I'll shelve it and then discuss. That is a very little, and it's just a modification of what we are doing. So we'll end here and then, okay, we'll just finish it in our next meeting and then write a test to end the whole semester work. Okay, so this is why I draw the curtains on today's meeting. Thanks for your time. And then, take care, and we'll continue on Friday. In fact, bye-bye to all of you.
Bye.
Good night.
Bye.
All right. Yo.